5 alternating series. This is the second video. We're looking at the alternating series remainder and absolute versus conditional convergence. So the alternating series remainder. If a convergent alternating series satisfies that condition, which it must, because the alternating series test requires this condition, then the absolute value of the remainder, Rn, involved in approximating the sum S, where S is the actual sum of the series, by Sn, where n is just Sn, uses n terms of the sequence to find the sum, to approximate the sum, is less than or equal to the first neglected term, right? So this saying capital S is the actual sum, S sub n is an approximate sum. The difference between the two is less than or equal to the next sequence, next item in the sequence. Basically the first item that is which is not being used to approximate the sum. So when approximating the sum of an alternating series that has been confirmed to converge, it does have to converge. Okay? The approximate error is the absolute value of the first term being left out. Right? Remember, if I have S sub n, or the sixth, I'm adding up from 1 through 6, then A sub 7 is the actual error. Right? So if Sn is the approximation of the series, then the error is at the most A sub n plus 1. For example, if S sub 8 is the approximation, then A sub 9 is the greatest error. Okay. Let's see this in action. So we're going to approximate the sum of the following series. This is one you haven't seen before, huh? All right. So this is an alternating series, and so there's no well, at this level there's no way to get an actual sum for this. So best we can do is approximate it. Right? It's an alternating series, and A sub n plus 1 is less than or equal to A sub n. You can see that, right? 1 over n, 1 over, that's 1, 1/2, 1/6, 1/24, 1/120th, 1/720th, blah, blah, blah. All right? And definitely the terms are going to 0, so it converges by the alternating series test. So the first 6 terms, so we're going to add up the first 6 terms, is 91 1/44th, or 0.63194. So this is using A sub 1 minus A sub 2 plus A sub 3 minus A sub 4, yada yada yada. So this is the sum of the first 6 terms, right? And we're going to do this 0.63194, 10 hundredths, thousands, 10,000, hundred thousands, 1 millionth, 6. Okay. So sum of the first 6 terms is that. We want to use the alternating series remainder to approximate how far that is, how far that's possible from the actual, right? So A sub 7 is the next term in the sequence, which would be 1 over 5040, which is approximately 0.0002. All right. So this is the greatest error, right? And this is the current approximation using S sub 6. So the actual sum lies between, you subtract the 0.0002 from that and add it, and it's between these two numbers. So it's between those two numbers. So our sum is between these two values. Right? And this is only taking 7 terms of the sequence, and we got a pretty good estimate. Right? We're correct up to 10 hundredths thousandths place after only 7 terms. Right? Well, after only 6 terms, using the 7th term as the approximation. All right. Now on to absolute and conditional convergence. Right. So remember, we had the harmonic series divergent, but when we alternated, it converged. So that's what's talking about here. So sometimes it's easier to see if the absolute version converges. Right. And if the absolute version converges, then the alternate version also converges. And that's what this is basically saying, right? So it basically says if all the positive version of a series, okay, if the all positive version, in other words, it's not alternating, of a series converge, then version where the sign changes will also converge. Okay, By the way, though, it doesn't have to be an alternating series. Remember, you can have series where it goes positive, negative, negative, positive, negative, and that's not considered an alternating series. But if we just take the absolute value of it and that series converges, then we don't have to have an alternating series test. We could just say, well, if the positive version converges, then the one that's where the signs change will also converge. So the definition of absolute and conditional convergence. So if the all positive version converges, then the series absolutely converges. In other words, if we take the absolute value version and it converges, then the series absolutely converges. If the series converges but the all positive version diverges, in other words, you have one that's sign changes, right? If the series so when we talk about if the series converges, we're talking about a series where the signs are changing. And we take the all positive version, but the all positive version diverges, then the series is conditionally convergent. All right. Okay, so let's look at some. So we're going to determine whether each one is convergent or divergent, just in general. Right? And then if it converges, we want to know if it converges absolutely or conditionally. Okay, so this is the term, right? We take the limit as n goes to infinity. N factorial is going to overpower 2 to the n. So the limit does not exist. So this just diverges anyways, right? By the nth term test for divergence, this series diverges. So this doesn't converge at all. Just let it go. All right. All right, determine whether each of the series converge. Okay, same directions. This time we have square root of n, 1 over square root of n. It's an alternating series, right? It's going from negative, positive, negative, positive. And this is true. A sub n plus 1 is less than or equal to a sub n. It's consistently going down, right? That's pretty obvious. It's only a difference by plus 1 in the denominator, but that makes this fraction smaller than this fraction. All right. And the terms are going to 0. So the series converges by the alternating series test. But if we drop the negative 1, and we're taking the absolute value now because we're testing to see if it's absolutely convergent. All right, we take the absolute value, then we get this, which is n to the 1/2. So this is now just a regular p series. Right? The p series, p is 1/2. So by the p series test, the absolute value version diverges. Right? Since the absolute value version diverges, but the alternating version converges, this is conditionally convergent. Right? The original version, the alternating version converges, but the absolute value version diverges. Thus, the series conditionally convergent. Another example. Same thing. We're going to do basically the same thing. Now, this one is not considered an alternating series, because it's not going back and forth consistent. It doesn't have the positive, negative, positive, negative, positive, negative. This is like negative, negative, positive, positive, negative, positive, positive. You know, it's not consistent. It's not all even ones are negative or all odd ones are negative. So it's not considered an alternating series test. Okay, so you can't use the alternating series test. However, if we took the absolute value of that, and then it turns into a geometric series. Right? If we just get rid of that negative 1 to that weird looking power, it turns into the geometric series. And for the geometric series, this is a convergent geometric series because the r is 1/3. Well, then if we take the absolute value version and it converges, then the semi-alternating version, the one where the signs are changing, that's going to converge as well. So this is an absolutely convergent series simply because the absolute value version converges on its own. Okay? So this is absolutely convergent. Okay. Another one. Let's look at this one. This is an alternating series. Let's check out the first condition. Limit as n goes to infinity. That expression goes to 0, so it passes the first condition. Second condition, we just compare, right? If you plug in n plus 1 into that, you get n plus 2. So it's off by a little bit, but anyway, that's all you need, just to be a little bit off. It doesn't have to be a big amount. So this is still smaller than that, so it meets condition 2. So by the alternating series test, this series converges. Let's look at the absolute value version. If you take the absolute value version, in other words, just get rid of that negative 1, and you get this, and this is not anything special. However, it's pretty easy to compare this to n, or 1 over n rather, right? We know that n is greater than natural log of n plus 1. Right? N looks like this. Or is it like this? Okay, then natural log just kind of goes underneath. Right? This is the graph. Yes, my arm is the graph. So the natural log kind of goes under that line. So if you flip it, you take a reciprocal, then the relationship is reversed. So 1 over n is less than 1 over natural log of n plus 1. All right, now this value, the 1 over n would make the harmonic series, and we know the harmonic series diverges. And if we compare this one, is bigger than the harmonic series. So by the direct comparison test, the absolute value version diverges. So this was an example of using a direct comparison test where I thought it was easy. You might disagree, but comparing n to natural log of n plus 1, I think it should be easy. Okay, all right. So by the direct comparison test, this series, the absolute value version, diverges. Therefore, this series converges conditionally. Remember the alternating series version, the one with this negative 1 to the end. That one converged by the alternating series test. This one diverges by the direct comparison test to the harmonic series. So this series converges conditionally. Hey, what do we cover? We cover the alternating series error, so we can figure out how far off we are when we use an approximation. And we define absolute convergence versus conditional convergence, right? All right. Sometimes finding the positive version is easier, right? Especially when the alternating part or the negative, the sign changing part is messed up or confusing. And we can just drop it and do the absolute convergence. Of course, if it doesn't converge, then we have to go back and check out the alternating version. Anyway, all right, so conditional convergence. This is... Right, this really applies to alternating series, like the harmonic series, right? It converges only when it's alternating. All right, that's it. Have a good weekend.